Hi students, I'm going to work a Unit 5 review for AP Calc AB, and I am using Tony Records' Unit 5 review that he has posted, and he's a teacher at Avon High School, I believe in Indianapolis, Indiana, and I'm going to work through as many of these problems as I can for you. The first set of problems, 1 through 6, are calculator active. I could probably do most of these and should do most of them without a calculator. Number 1 says the graph of the twice differentiable function f is shown in the figure. Which of the following correctly orders the f of 2, f prime, f double prime? So we'll come over here to 2 and we'll draw some conclusions about this. All right, so we know that f of 2 is 0. We know that f prime at 2, which would be the slope of the tangent line, has to be negative because it's decreasing, but it looks like it's in the concave up section of the f of x, so it has to be a second derivative that would be positive to reflect that it's concave up. Therefore, my smallest value would be f prime, followed by f of 2, and then f prime. So we have to go with letter C. Let's go to number 2. A rectangle is bounded by the x and y axes, and the graph of y equals 6 minus x over 2 as in the figure below. What length and width should the rectangle have so that its area is a maximum? What I'm going to do is I'm going to write an equation for area. The area of this rectangle is going to be x. So in this figure, what I'm doing here is I'm saying that if this distance here, which can vary depending on where we place this right edge of the rectangle, we'll call that x right there. And since the equation of that line is 6 minus x over 2, that means the height of the rectangle is the y coordinate or the y value of that function. So that height of the rectangle is 6 minus x over 2. Well, that's going to give us an area function that is x times 6 minus x over 2. We're trying to find a maximum value of that. If I distribute the x through here, that's going to give me 3x minus x squared over 2, because 6 over 2 is 3. X over 2, distribute the x, that's what you get. If you take now the derivative of that, in order to find its critical value, that's going to be 3 minus x when I take that derivative. When I set that equal to 0, I do get x equals 3. So that means that I'm going to reach a maximum. That's the only critical value. It is going to be a maximum, so x is going to be equal to 3. And when I plug that into the height, I get 3 halves, or 1.5. So my answer here is D. Number 3, let f of x be a strictly increasing function such that f of x is negative for all values of x. Let g of x be a strictly decreasing function such that g of x is greater than 0 for all values of x. If h of x equals g of x, if h of x is f of x times g of x, which statement is true? Well, they're asking me questions here about what is h of x doing, increasing or decreasing. And the only thing that I could use to judge that by would be taking its derivative. That requires me to use the product rule. So that's going to be f prime of x g of x plus f of x times g prime of x. Well, I need to know some signs for all of these things. So let's consider f of x. So f of x is negative, it tells us in the problem, but it also tells us that f of x is increasing. So that means its derivative must always be positive. For the g of x function, they told us that it's a strictly decreasing function, but it's also positive. So g of x is positive always, but its derivative must be negative since it is a strictly decreasing function. So if I put the signs in to my first derivative for h of x, f prime, so let's do that. So f prime is a positive, g of x is a positive, f of x is a negative, g prime is a negative. So I have the product of two positives added to the product of two negatives, which would be positive. So this has to be a positive. So this tells me then, this conclusion here says that while I don't really know the number for h prime, I do know that it does have to be positive based on the signed math that's going on right here. So that means that h prime has to be increasing. And what else would we know here? So we know that it is, so it can't be decreasing. Its derivative is positive. What else do we know? So the product here, f of x is negative, g of x is positive. So h of x itself has to be, h of x would be a positive times a negative. So it has to be less than 0. So h of x is less than 0, but strictly increasing right there. That's going to be our answer. Number 4, a right circular cylinder can be used to design, is to be designed to hold 22 cubic inches of a liquid. The cost for the material for the top and bottom of the can is 2 cents per square inch, while the cost for the material of the side of the can is 1 cent per square inch. Let R represent the radius and H the height of the cylinder. The lateral area of the cylinder is this, while the tops would be the circle right there. And then the volume is given by this. Which of the following represent the correct primary and secondary equations in order to minimize the total cost of manufacturing the can? So this is an optimization problem. The primary formula that we're going to be using here, since we are trying to, what does it say that we're trying to optimize? To minimize the total cost. So the total cost of the can is what we're trying to minimize. So that is to be a cost function, right? So it's going to be a cost. So yeah, we're going to take 2 cents, and that's going to be for the side, and that's the 0.02 times 2 pi RH. And then we have to add to that the cost of that's 1 cent, isn't it? That's going to be 0.01. Because the sides only cost 1 cent per square inch. That would be the square inches of the sides, but then we're going to pay 2 cents for the tops and bottoms. So that's going to be 2 pi r squared, because I have 2 circles on the top and bottom. So you can see, if looking at these primary equations, it looks like that's valid and this one is valid. These two are not valid because they left out the fact that there's both a top and a bottom. So they needed to double the pi r squared. The secondary equation is going to be the volume, right? So that's going to be pi r squared h. Oh, okay. So they got, both of those have the right secondary equation. 22 is equal to pi r squared h. What is the difference between these two is whether they had the right unit cost attached. So the sides are cheaper, and they were 1 cent. So yeah, this looks like answer C. Let's move to number 5. The graph of h of x is shown above. Which of the following could be the graph of h prime of x? So this being h of x, what I notice about h of x first, if I'm going to compare it to its derivative, I notice that it does have critical values there, and it's a max followed by a min. So that means this has to have 2 x-intercepts on the derivative function to reflect that the derivative is going to be 0 at those 2 points. So it could be either B or D. Now, because this is a relative max, the derivative has to go from positive to negative at the x-intercept, right? Because the function here to the left of that relative max is increasing. Then it's followed by a decreasing portion right there. When it's increasing, the derivative has to be positive. When it is decreasing, that's when my derivative is going to be negative. So it has to go from above the x-axis to below. That's going to be letter D. Okay. The other thing you can do is, if you should be able to recognize that as a likely third degree polynomial with a positive leading coefficient. Therefore, its derivative would be a second degree polynomial with a positive leading coefficient. And the only graph there that reflects this, a quadratic that opens upward, is D. Okay. But again, I was focusing here on the fact that if my derivative has x-intercepts, those are critical values. That would be a maximum x value. That would be a minimum x value. And again, that's because the derivative is going from above to below, from positive to negative, meaning from increasing to decreasing on the original function. Number 6. The figure below shows the graph of f prime, the derivative of the function of f, right? So you want to make sure you prominently, I know it says it there, but we're focusing on the fact that it's f prime. And from -7 to 7, the graph of f prime has horizontal tangent lines. Yes, it does. At -3, 2, and at 5, and a vertical tangent at x equals 3. Find all values of x on that interval at which f attains a relative minimum. Well, it's going to attain a relative minimum when this derivative changes from a negative to a positive. So right here, right there. So I would say here, I'll say f of x has a relative min at x equals -1, because f prime of -1 equals 0, and f of x changes from negative to positive. So again, since the y-axis here is measuring the derivative values, at this point, to the left of -1, the derivative is is negative because it's below the x-axis, but then after -1, it's positive. So that means that f of x would have been changing from decreasing to increasing at -1. Letter B says, for all values of x on the interval, find all values at which f attains a relative maximum. And that's going to be at x equals -5, because again, my derivative is 0 here at -5, and it is changing from a positive to a negative value. So that means f of x was changing from increasing to decreasing at x equals -5. So this is my statement. F of x has a relative max at x equals -5 because f prime of -5 is 0 and f prime changes from positive to negative. Up here on this one, this should be f prime changes, right? Because what we're noticing here at -1, f prime is changing from a negative to a positive at x equals -1. Letter C says, find all intervals for which the second derivative is negative. Well, the second derivative is the first derivative of this function, obviously, because this is f prime. So f double prime is going to be its derivative. And the second derivative is going to be, they're asking us for when is the second derivative negative. It would be over intervals where this function is decreasing. And where is this function decreasing? From -7 to -3, and then it increases after that. When it gets to 2 at that relative max, it starts to decrease until it gets to 3. And it's got a vertical tangent line. So we'll split this up into from 2 to 3 and then from 3 to 5. That's going to be the 3 intervals over which the function is decreasing. F double prime of x is less than 0 over the intervals -7 to -3 and 2 to 3 and 3 to 5, because f prime of x is doing what? Because f prime of x is decreasing. That is our justification. Part D says, find all values of x over the interval where f of x has a point of inflection. Justify your answer. Now, the question becomes, how do I identify points of inflection for f of x when I'm looking at the f prime of x function? What I'm looking for are relative extremes. Here, here, and here. At those x values, x equals -3, x equals 2, and x equals 5, f of x has to have a point of inflection. Now, why is that? Because if my f prime changes from decreasing to increasing, that means that the second derivative just changed from being negative to being positive, because the sign on the second derivative tells me the direction of its predecessor, f prime. And this means that the function f of x would be changing from concave down to concave up. Similarly, here at x equals 2, my f prime changed from increasing to decreasing, and at x equals 5, it changed from decreasing to increasing. So those are locations where the second derivative is changing signs. And when the second derivative changes signs, the concavity is changing from negative to positive or positive to negative. So we're going to go ahead and write that up. So f of x has points of inflection at x equals negative 3, 2, and 5 because f double prime of x changes. And actually, I'm going to state this in terms of my function that I'm examining, right? So I want to change it and describe what I see in the f prime of x function, because that's the one that they want me to base this explanation off of, because f prime changes from decreasing to increasing or increasing to decreasing. And that completes then problem number 6. Let's move on to number 7. We're now moving to the non-calculator portion. Notice on the calculator portion, I never touched the calculator. Number 7, which is common. Well, I'm not saying that's common, but it is common to not use a calculator on a calculator active problem. Usually on a calculator active section of a test, you'll use it at least once. It just so happened we really did not need it there. Number 7 says the graph of the second derivative of a function f of x is shown. Which of the following would be true? So we have to analyze each one of these. Number 1 says the graph of f would have a point of inflection at x equals negative 1. Well, if this is the second derivative, it is changing signs there. So I think that's going to be true, because if f prime changes from positive to negative or vice versa, that's going to be the location of a point of inflection for f of x. Number 2, the graph of f of x is concave down on the interval negative 1 to 3. So from negative 1 to 3, we see that f double prime of x is negative, so therefore f of x has to be concave down, so that is true. This says, if I can read this correctly, the graph of f prime would be increasing at x equals 2. Well, at x equals 2, this is registering a negative value, right? So f double prime of 2 is a negative value, which means that f prime is concave. Sorry, it tells me that f is concave down, but it would also tell me that the predecessor to the f double prime, which is f prime, would have to be decreasing, right? When its derivative, when f prime's derivative is negative, that means that f prime has to be decreasing. So that is false, and we're going to go with C. Number 8 says, given the graph of the derivative of f prime, notice it's not labeled over here. So this is our f prime of x. Which of the following would correctly depict a possible graph of f of x? Well, let's see. This tells me that we have this vertical asymptote here on my f prime. And notice out on the extremes, f prime is approaching 0. So f of x would have to be flattening out. And it does that, really, on both sides here. However, one thing to keep in mind about this here, that if f prime is approaching 0 over here on the left side, but it is less than 0, right? In other words, this thing is underneath the x-axis. That means my derivative is negative, so it's decreasing. And over here, it's above, but so that means that f would be increasing. So it's got to be decreasing on the left, increasing on the right. So that takes this one out. And this one, that wouldn't be it, because it has to be decreasing. That's an increasing section right here. All right. This one here looks like it would be it, because this has to be negative slope. This function's decreasing, and then over here it's increasing. So it looks like B is our choice. There's our choice for B. And again, I'm noticing that because f prime is positive, over here, f of x has to be increasing. Over here, to the left of that asymptote, f prime is negative, so f of x has to be decreasing. And the only one that shows that would reflect decreasing on the left, increasing on the right, is graph B. Number 9. Use the graph of f on the right to estimate the value of C that justifies the mean value theorem for the interval 0 to 7. Well, here's x equals 0. Here is 7. So it looks like what we would do, to estimate the value of c. All right, so that means then that this would be the secant slope. I'm looking for a section on this graph whose tangent line slope would be parallel to that. So let's just take these one by one. 3.7 would be about here. That I'm not sure about that. That could possibly, it does look like it has positive slope. So I'm going to say that's a possibility. Let's see if we can eliminate any of these. At 4.3, there's no way because that's got a negative slope. At 5.5, here's 5, there's 5.5. That also is a slightly negative slope. And at 7, yeah, that tangent line, that's very steep. So it looks like that has to be the one where the at 3.7, again, that would be here's 3. 3.7 would be about here. You can see that the tangent line slope there would be approximately parallel to that secant slope. Number 10. Engineers are designing a box-shaped aquarium with a square bottom and an open top. The aquarium must hold 500 cubic feet of water. Which of the following represents the correct primary and secondary equations in order to find the dimensions they should use to create an aquarium with the least amount of glass? Well, what are we trying to minimize or maximize? The least amount of glass. So one of the things that you do have to know about these optimization problems is that when they talk about the amount of a quantity that's in some kind of a container, that really is surface area. And so what we want to do is our primary equation is going to be our surface area equation. So what would be the surface area formula for this? The surface area is going to be the top and bottom area, which would be x squared, but times 2, because you have a top and a bottom. The sides, of which there are 4 in the box, their areas are xy, and there's 4 of them. So that surface area equation should look like that. And do we see one of those? Oh, let's see. It's an aquarium with the least amount of glass. So I think then, yeah, open top. I missed that. So there's really only there's only a bottom. So it is going to be x squared plus 4xy. So it looks like that's going to be our primary surface area right there. The volume is x times y, and that has to be 500. So yeah, so number 10 would be the answer B. Number 11 says, identify the open intervals on which the function f of x equals x squared minus x minus 12 is increasing. Well, I'm going to take the derivative, which gives me 2x minus 1, and I'm going to set that equal to 0 to find the critical values for my function f. That would give me a critical value of 1/2. Therefore, if I do my number line analysis here, 1/2, and I choose a test point to the left of 1/2, we'll call it 0, to the right 1, and I'm going to check the sign on f of x for those two test points, 0 and 1. When x is 0, my derivative is going to be negative, and when my x is 1, that's going to turn this to be a positive. So that tells me that f of x is changing from decreasing to increasing at that critical value of 1/2. So we would be increasing from 1/2 to infinity. Now, this could have been answered without calculus. I hope you noticed that because this is a parabola. If you know x equals negative b over 2a, which is the formula for the x coordinate of the vertex, then using the coefficients here, b is negative 1, a is 1, then you do get an x coordinate of 1/2. And I know that the parabola is opening up, so it has to be opening up. That's an x coordinate of 1/2, so everything to the right of 1/2. There you go. Answer D for number 11. Number 12, suppose f of x is differentiable everywhere, and f prime of negative 2 is negative 5, and f prime of x is less than or equal to 5 for all values of x. Using the mean value theorem, what is the largest possible value of f of 8? Now, occasionally you run into these problems that seem unfamiliar. Like maybe you say, I've not worked one of these kinds of mean value theorem problems before. Well, the thing that you can do is go to the mean value theorem formula. Here's the mean value theorem. There's the theorem, the mean value theorem in a formula. And the mean value theorem says that if my function is continuous, then that would mean that if you pick an interval of x values over which the function is continuous and differentiable, then the secant slope, right? This right here is the average rate of change. Also, we call that the secant slope between those two x values. Then there has to be at least one value of x equals c for which the instantaneous rate of change, that is the tangent line, we could think of that as tangent slope at a particular point on the curve. There has to be at least one value c such that the instantaneous rate of change is equal to the average rate of change. So what I could do in this problem is I could just set this formula up. And it is differentiable everywhere, so that means it is differentiable and continuous. So they tell me that f prime of x is less than or equal to 5. So what I'm going to do is I'm going to say then that they're telling me that f prime of c has to be less than 5. So that means that this fraction has to be less than or equal to 5. That the average rate of change needs to be less than or equal to 5. Well, let's fill this in. It looks like my interval would be x equals 8 and x equals -2. Those are the two x values in question. So then I'm going to set this inequality up and write it like this. F of 8 minus f of -2 over 8 minus -2 has to be less than or equal to 5. Well, let's plug in what we know. Well, we don't know f of 8, right? We're trying to find f of 8, so we really don't know what that is. But f of -2 is -5, and 8 plus 2 is 10. That's less than or equal to 5. What we can do is multiply both sides of that inequality by 10, and we'll get f of 8 plus 5 has to be less than or equal to 50, and then I will subtract 5 on both sides. So it looks like f of 8 must be less than or equal to 45. So 45 would be the maximum value for f of 8. So again, when you come across that unfamiliar problem, if you can connect it back to a formula for the theorem you're using, that at least gets you started where you might have a chance to get yourself an algebraic solution. Number 13, for all x in the closed interval 2 to 5, the function f has a positive first derivative. Okay, so that means that f must be increasing, because if its derivative is positive, then f must be increasing, and it has a negative second derivative. That means f is concave down. Well, let's get rid of any of these values that don't show f being an increasing function. So we can get rid of c and d because these y values are on the decline. So that's a decreasing function. Now, what characterizes a function that is concave down? Most of my students, I explained this to you when we were in, well, I guess it's really a pre-calculus thing is where we show this to you. But what characterizes the concavity of a function? I think you all would agree that that's concave down. As you move left to right on a function f that happens to be concave down on a certain interval, what happens is the slopes are decreasing. I'm talking about the tangent slopes. If you were to take a look at little slices on this curve and draw little slopes, you would see that this is a positive slope, but they're getting less positive on this concave down section. So what happens is your derivative is decreasing. Okay, so that would mean then that if you looked at these y values, I expect there to be a decreasing rate of change. So 7 to 9 is an increase in 2. 9 to 12 is an increase in 3. 12 to 16 is an increase in 4. That's going to be a concave up section of f of x. Compare that to this one. That is an increase in 4. It's an increase in 3. It's an increase in 2. So in that case, the average rates of change as you're moving left to right are decreasing. So b, while both a and b are increasing functions, the y's are going up, they are increasing at a decreasing rate on b, and that becomes my answer. 14. On the closed interval from 0 to 2 pi, the absolute minimum of this function f of x equals e to the sine x occurs at what point? So this is a candidate's test. The candidate's test says we're going to, as long as my function is continuous over this interval, the absolute extremes are going to occur at the endpoints or at any critical values that are inside that interval. So we need to find critical values for this function. So we will take its derivative. The derivative of an exponential is itself times the derivative of the exponent, which would be cosine of x. So to find critical values, you set that equal to 0. If you set e to the sine x equal to 0, there are no solutions to this. If you took the natural log on both sides to get rid of the exponential, you can't take the natural log of 0. There's no solutions to this. Over here, setting the other factor equal to 0, cosine x, yeah, over this interval, I'm going to get two values actually. I'm going to get cosine is 0 at pi over 2 and also at 3 pi over 2. So what I have to do is add those to my candidates where I would have absolute extremes over the interval. Then what your job is to plug each of those candidate x values back into the original function to calculate the y coordinate at those x values. So when x is 0, that's going to be e to the sine 0, which is 0, so that's a 1. This would be e to the sine of 2 pi. Sine of 2 pi is 0, so that's 1. If x is pi over 2, that's e to the sine of pi over 2. Okay, sine of pi over 2 is 1, so that's e. And then here, e to the sine of 3 pi over 2. Well, 3 pi over 2, sine of 3 pi over 2 is a negative 1. So that's e to the negative 1, or 1 over e. E is 2.718, approximately, right? Because it is an irrational number, but it's approximately 2.718. We're looking for the absolute minimum. 1 over e would be 1 over 2.718. Which one of those is the smallest number, the smallest y value? It looks like this is going to be the winner right here. So that means that at 3 pi over 2. So C is my answer. Moving on, number 15. Let g be the function given by g of x equals x squared times e to the kx, where k is a constant. For what value of k does g have a critical point at x equals 2/3? Well, critical points are where my derivative is equal to 0, or where it would be undefined, given that those are in the domain of the function. So I need to take this derivative and set it equal to 0, and then ultimately solve for k. So let's take this derivative. To take the derivative of g prime of x, I'm going to have to use the product rule. I'll take the derivative of the first times the second. I'll add to that the first times derivative of the second, and I will set that equal to 0. So just reviewing that this is the product rule. I took the derivative of the first times the second plus the first times derivative of the second. Notice by the chain rule, the derivative of e to the kx is itself e to the kx, but then times the derivative of k times x. K is a constant, so the derivative of kx is just k. And now I'm going to solve this for k. Well, I'm going to solve this like most nonlinear functions that I solve when I have 0 on the other side. I'm going to solve it by factoring. So I'm going to factor out the greatest common factor between the two terms that came about from this product rule. It looks like I have an x and I have an e to the kx that can be pulled out. That makes this one a 2 plus, that's going to leave me a k times x, like that. If I did that right, equals 0. So for what value of k does g have a critical point? Well, gee, I'm not sure that at 2/3. All right, so what I'm going to do now is say, well, for this equation to be true, I could set these two equal to 0. If I set x equals 0, that doesn't really help me because it doesn't have k. If I set e to the kx equal to 0, there's no solution to that. Here, I'm going to set 2 plus k times x equals 0, but I'm going to plug in 2/3 for x. So this becomes 2 plus 2/3 times k. And now I will solve this for k. So I will subtract 2 and then multiply both sides by 3/2. it looks like k, these will cancel. This is going to be a -3. I really like A as my answer. Moving on to number 16. The maximum value of f of x is this. The maximum value of f of x on the closed interval 0 to 4 is. This is going to be another candidates test. My first two candidates are the endpoints on the closed interval. I do need to find any critical values that exist in that interval. We'll take the derivative and set that equal to 0 to find the critical values. We'll factor a 6 out, and then we'll factor that quadratic. The solutions, therefore, are 2 and 3, and both of those critical values are within the interval in question, so we will add both of those to our list of candidates. Now our job is to go ahead and calculate what would be the maximum value here. So when x is 0, that's going to be 0. I'm going to have to do a little bit of mental math here. So when x is 4, 4 to the third is 64 times 2 is 128. 4 squared is 16. I can't believe I have to do this, but it looks like we need to take 15 times 16. So that's going to be 95, 1. So that's going to be 240. Okay, so let's go back here. So that would be 2 to the third. No, we're still working on this. So that's a 240 minus 240 plus 36 times 4, 144. So what does that give us? It looks like an answer of 12, perhaps? That looks like, no, this should be 32. Let's see if that's right. 128 and 144 is 272 positive. Yeah, so 272 minus 240, 32. All right, just speeding things up here. If I let x equal 2, I'm going to get a 28. If I let x equals 3 and plug that in, I should get a 27. I'm looking for our maximum value. It ends up being 32 as our answer right there. Number 17. Consider the function f defined by this, where first and second derivatives are given by this. So they went and did us the favor of giving us the first and second derivatives. It says use f prime to find any critical numbers. Well, I'm going to set the f prime equal to 0. And when I do that, that f prime will be 0 when the numerator is 0. So I get x equals 0 would be a critical number. Now, keep in mind that when you've got a rational function, you have to consider any values that make the first derivative undefined. So that would mean anything that makes your denominator 0. Well, there is going to be no number that makes my denominator 0 because that x squared plus 3 will always be positive. If you weren't sure about that, if you just set the denominator equal to 0 and solve it, you would take the square root of both sides, giving you x squared plus 3 is 0, subtract 3, and then when you square root both sides, you'd see that you have the square root of a negative number, so there's no real number. So the only critical value would be 0. Notice it doesn't say to justify or explain. So just to give the answer of x equals 0 is going to be adequate for that free response question. Most of the time, they'll ask you to justify it, but really, this is the justification, right? That f prime of 0 is 0. B, construct a chart or number line and use the first derivative test to state the intervals of increasing and decreasing and state the location of any relative extremes. Well, here's going to be my chart and my number line. Now, normally on free response questions, they don't ask you to construct a chart, right? It says chart or number line. So yeah, I'm going to use my number line. And I'm going to plot my critical value, which is 0. Now, there are no vertical asymptotes, right? My denominator is never 0 of the original function. So I don't need to worry about there being any other intervals other than the intervals created by the split of my critical value. So I'm going to pick 1 and -1. And then I want to know what is the sign of the derivative at those two critical values. When I go to my f prime, when x is a -1, keep in mind my denominator will always be positive no matter what x value I put in there, because first of all, the x is being squared and added to 3, and secondly, the whole thing is squared. So it's going to be a positive. But so therefore, when x is -1, my numerator is negative, so f prime would be negative. When x is 1, the first derivative will be positive. So I would make the two following statements. I would say that f is increasing from 0 to infinity because f prime is positive, and f is decreasing from negative infinity to 0 because f prime is negative. It also wants us to state the location of any extreme values and the location of any extremes. Well, because I know the sign on my derivative, I know the direction of my f of x. It changed from decreasing to increasing, because if its derivative is negative, that means the function itself was decreasing. So that means I have a relative min. So the other statement that I would put here is the following. I would say that f has a relative min at x equals 0 because f prime of x changes from negative to positive. Part C says solve f prime of x equal to 0, f double prime. When I set f double prime equal to 0, the only thing I have to solve for is that when the numerator is 0. And that's going to give me 1 minus x squared is 0. And so the two solutions are plus and minus 1. Part D. Construct a chart or number line and use the test for concavity to state the intervals of concavity and state any points of inflection. Well, what we have here are the critical values of f prime, right? So when I set the second derivative equal to 0, those two are the critical values for its predecessor f prime. So what I'm going to do is I am going to plot those 2 points here, -1 and 1. And I want to know the sign of the second derivative for points in the intervals. So we'll use a -2, we'll use a 0, and we'll use 2. And we're going to calculate the sign of the second derivative function. Again, looking at the second derivative here, the denominator will always be positive because x squared will be a positive number. And if a positive plus a positive is going to be positive, so denominator is always positive. So the only thing we're really checking is what's the sign on the numerator. When x is equal to -2, that is going to make this quantity, the numerator of my second derivative, it's going to make it negative because it would be a positive times a negative. When it's 0, it's going to turn to a positive. When x goes to 2, it turns back to negative. That tells me something about f of x, meaning it was concave down, followed by concave up, and then followed by concave down after it gets past the number 1 right there. And state and determine intervals of concavity. So I would make the following 2 statements, and I'll put those right here. The first one is that f of x is concave down over the intervals -infinity to -1 and 1 to infinity because f double prime is less than 0. So I'm just saying that my intervals go from -infinity to -1 and from 1 to infinity. But then I could also state where it is concave up. F of x is concave up on the interval -1 to 1 because f double prime second derivative is positive. It also asked me to identify any points of inflection. Well, both of those would be points of inflection because the concavity is changing. So I would say, I'm not going to write this out here, but I would say f of x has points of inflection at -1 and 1 because the second derivative is changing signs. When you are writing these statements, right, be sure that you are telling what function you are referring to. Like, don't say it is concave down, right? So I need to say f of x is concave down because I need to specifically tell which function I'm talking about that is negative. I can't say because it is negative. There's 3 functions involved here, f prime, f double prime. So you have to specify which one you're assessing. Now, E says construct the graph of f on the coordinate plane to the right. Well, so let's take a look at what's happening here. We determined that we do have a relative minimum at x equals 0. Now, we don't have any specific points. Actually, we do, right? When x is 0, f of 0 is 0. So it has to have a relative minimum at 0, 0 right here, right? F of 0 is 0. Then what has to be happening is the function has to be decreasing to the left, but yet increasing to the right, and it needs to be concave down. So it would have to look something like this, like that. Now, the thing about it though is that my derivative does exist, right? If you come back up here and look at the first derivative, at x equals 0, the derivative is 0. So I need to actually not put a cusp there. So it has to look something like this, students. It would have to be something where it reached a minimum. Let's do it this way. I think I have a better idea. We had points of inflection at -1 and 1. So we're going to have to do it something like this. It's going to change concavity. In other words, it's going to be concave up here, but then concave down. So it would maybe do something like this. So you have to reflect that you've got this absolute, or I should say relative minimum, 2 points of inflection, and it always has to be decreasing to the left, but yet increasing on the right. So that would be something that would meet the criteria of everything that we just found. And that is a really good free response question because it's multiple parts, it builds on itself. You have some relatively easy ones up front. Probably most students will struggle with maybe getting that graph completely correct. As you see, I struggled a little bit there with gathering all the information I needed to make an accurate picture. Okay, from here then what I want to do is I've got a few questions that students had asked me about that they sent to me, and I'm going to include them on this video. So let me pull those up and I'll go over those. This problem that came from AP Classroom is from Unit 6. If your class has not yet gotten to Unit 6, then you probably don't know even what this nomenclature is over here. This is an antiderivative, and the student struggled with this one and made what I would consider is maybe a very classic mistake as students are beginning to learn antiderivatives. One of the things that we know from our derivative unit is that we know that the derivative of the natural log of x is 1 over x. This symbol right here is an antiderivative. This is saying to take the antiderivative of this. So students know that because the derivative of natural log is 1 over x, the antiderivative of 1 over x dx would be the natural log of x. And we put that in absolute values like that, plus c. Again, I think many of you watching this video may not yet be at Unit 6. But a classic mistake is to say, well, because this is in the denominator, then this must be the natural log of this, and that is not at all correct. But you'll be going over this in your class. Notice that all three of these other options are arctan, because one of the things we know about the arctan, or the inverse tangent function, is that, let's talk about in terms of a derivative, right? The derivative of arctan of, and I'm going to use, well, I'll just use x. Arctan of x is 1 over 1 plus x squared. So therefore, the antiderivative of 1 over 1 plus x squared is arctan. And you have to recognize that that's what this function is, that it is going to be an arctan because of the way that this is set up when you relate it back to what you know the derivative of arctangent is, right? You have to be on the lookout for things that look like a constant on the top, binomial on the bottom with an x squared. Probably going to be an arctan. However, what I need to do is I am going to have to set this up by factoring a 4 out of the bottom. So I'm going to start this problem down here by factoring a 4 out. Now, why would I do that? Because I want this 4 to be a 1 so that I can use this antiderivative of 1 plus x squared. So I'm pulling a 4 out. Well, that's going to make this to be x squared over 4 plus 1 with a 1 and a dx. I will now pull the 1/4 out to the front of the antiderivative, and that leaves me 1 over x squared over 4 plus 1 dx. There's something else that you'll be learning about in this next unit. It's called taking antiderivatives with u substitution. And what I'm going to do is my next step is to rewrite this as, I'm going to write this as x over 2 squared plus 1 dx. Because you would agree that x over 2 the whole thing squared is x squared over 4, but this now lets me use the dummy variable u to represent x over 2. And again, don't worry if you're like, what in the world are you doing? I've never even heard of u substitution. You're getting there, right, over the next couple of weeks. So, but those of you that do know it probably recognize what I'm doing here. But when I let u equal x over 2 and I say du, if I take the derivative, that would be just 1/2 times dx, which means that dx is 2 times du. Then what I do is I use that information for u and du, and I make myself a new integral in terms of u. So I have the 1/4 there. X over 2 gets substituted with u. So this is going to be u squared down here plus 1. The dx is 2 du. So I replace it. The dx here gets replaced with 2 du. That 2 multiplier gets pulled out to the front to be 2/4 or 1/2. Now I'm left with 1 over u squared plus 1 du. Now I know I can take the antiderivative of that as the arctangent of u. So this becomes 1/2 arctan of u. But what was u? It was x over 2. So I'm putting x over 2 plus c. And that becomes my answer. And let's see if we have a match here. So this is going to be answer D right there. Now, the other way that you could do this too, we have to mention this, that if you knew that was an antiderivative and you're like, I'm not sure how to take the antiderivative, one of the things you could do is take the derivative of each of these answers using the chain rule and see which one gives you 1 over x squared plus 4. So you would have to know the formula for the derivative of arctan, but think about this. Here's why that's not the answer. If you use the chain rule to take that derivative, that would be 2x over x squared plus 4. And that's not the same as 1 over x squared plus 4. So that can't be the answer. The next problem that I'm going to work is a problem that's a free response that covers Unit 5. And we're just going to do this last part, the mean value theorem portion of this problem. In this problem, they are giving us the derivative of f over an interval, and they tell us that it is a twice differentiable function. And this says in part D that use the mean value theorem and explain why the average rate of change of the function f over the interval cannot equal 1.25. Well, the first thing that we have to state is that the mean value theorem does apply to this particular function and problem. And since f is twice differentiable, that means it is going to be continuous as well. So I will make that statement. Because f is twice differentiable, it is therefore continuous over the interval -2 to 2, and the mean value theorem applies. Now, there's a short way to do this, and there's a long way to do it. The short answer to this is that the mean value theorem says that there has to be in that interval from -2 to 2 an x value equal to c, such that f prime of c would be equal to the average rate of change. And they're telling us that it's they're showing that it can't equal 1.25. They're wanting us to show that that can't be true. Well, that would have to be the average rate of change. Well, what is f prime? F prime is a sine function, right? There is no way that sine could equal 1.25 because its range is -1 to 1. So I could just use that right there and say, because f prime of x has a range of -1 to 1, it is not possible for f prime of x to equal 1.25. And that would suffice. I would probably want to add to that, however, that therefore the average rate of change cannot equal 1.25 because the average rate of change would be equal to the f prime of c. Now, the other way to do this would be, it's quite a bit longer. You actually can calculate f prime. Let's see, I may be thinking of a different problem. I think we'll just stop right there. So that's all that we're really saying. Remember, I'll just kind of add this as a bit of an explanation to it, that we know that the mean value theorem says f prime of c has to be equal to the derivative, right? F double prime of b minus f double prime of a. No, sorry, f of b minus f of a all over b minus a, like that. Now, on the interval, we do know, yeah, we don't really know either of those values. So that kind of makes it difficult to do anything other than just say that this is average rate of change. And the average rate of change, right, there's no way that this is going to, that could actually happen, because this is a sine function. And that sine function, there's never going to be a value of c that would make it equal to 1.25. I think there's another problem that I was thinking of that was very similar to this, but it involved a second derivative. So, but anyways, that's going to be our explanation there. Notice that on a problem like this, it is very common, I would say 80% of the time when you're working a 4-part free response question, that part D is going to be by far the hardest question that's asked. They usually go in ascending order of level of difficulty. So by design, they want to give you an opportunity to get some easier points on parts A and B, and then progressively make it harder so that higher performing students have a chance to differentiate themselves from the lower performing students on those parts C and D. All right. Hope that helps, class. Good luck.